Ocean depth defines a vertical dimension that extends across the majority of the planet's surface. This dimension is structured by measurable gradients in pressure, temperature, and density that persist regardless of location. Vertical scale operates as a stable physical framework within which surface and abyssal conditions remain part of the same continuous column. The global ocean exhibits a wide vertical span, measured from the sea surface to the deepest mapped points. This span extends from 0 meters to depths slightly exceeding 11,000 meters. The maximum recorded depth occurs in the Western Pacific region and reaches approximately 10,900 meters. Most ocean areas occupy shallower portions of this total range. Shallow marine areas are commonly described as extending from the surface to about 200 meters. This upper interval corresponds closely with the depth of continental shelves. A distinct depth range lies between roughly 200 meters and 1,000 meters. 100 meters will be in part of 7 meters. Another broad interval extends from about 1,000 meters to 3,000 meters. Large portions of the ocean floor are located between 3,000 meters and 6,000 meters. This range contains the majority of abyssal plains measured by total area. Depths greater than 6,000 meters form a separate category, recognized in global classifications. These extreme depths are confined to narrow, elongated regions rather than broad surfaces. The full vertical scale of the ocean exceeds the average elevation range found on land. Ocean depth values are measured relative to mean sea level as a global reference. Depth classifications rely on numerical thresholds rather than regional naming conventions. These thresholds remain consistent across different ocean basins. No single depth range dominates all ocean regions equally. Some basins show gradual depth transitions, while others include abrupt numerical changes. The global ocean depth span is defined entirely by measured vertical distance. This span remains a stable reference framework for large-scale ocean description. The shallow water depth range occupies the uppermost portion of the global ocean vertical scale. This range extends from the sea surface to a depth of approximately 200 meters. The lower boundary at 200 meters is widely used as a numerical reference in depth classification systems. This interval is commonly referred to as the shallow water zone in large-scale descriptions. It is also associated with the continental shelf in terms of depth limits. Continental shelves typically terminate near the 200-meter depth contour. Not all continental shelves reach this depth uniformly. In some regions, the shelf edge occurs at depths slightly shallower than 200 meters. In other regions, shelf depths approach or modestly exceed this numerical threshold. The shallow water range remains defined by its upper and lower vertical limits. Depth values in this range are measured from mean sea level downward. The shallow water range represents the smallest vertical segment of the full ocean depth span. It's C on that. Despite its limited vertical extent, it covers extensive horizontal areas along continental margins. Global maps often display this range as a broad band adjacent to landmasses. The shallow water range is present in all major ocean basins. Its areal distribution varies depending on continental configuration and shelf width. This depth range is numerically distinct from deeper classifications used elsewhere. The transition beyond 200 meters marks a change in depth category designation. Shallow water depths are identified solely through vertical distance measurement. The upper ocean boundary is fixed at 0 meters by definition. The lower boundary remains standardized across international depth references. The shallow water depth range serves as a consistent vertical reference interval in ocean classification. The intermediate depth range occupies a middle segment of the global ocean vertical scale. This range is commonly defined as extending from approximately 200 meters to 1,000 meters. The upper boundary aligns with the lower limit of shallow water classification. The lower boundary marks a transition to deeper depth categories used in global references. This interval is often labeled as an intermediate or mid-depth range in ocean depth frameworks. Numerical limits remain consistent across major ocean basins. Depth values, in-depth, is sensitive across major ocean basins. The intermediate range represents a vertical span of about 800 meters. This depth range occurs beyond the continental shelf edge in most regions. It is present along continental slopes and adjacent deep sea areas. The horizontal extent of this range varies widely between ocean basins. Some regions display broad intermediate depth zones, while others show narrow bands. Global bathymetric charts consistently identify this range using depth contours. Standard mapping frequently uses the 200-meter and 1,000-meter lines as boundaries. These numerical thresholds allow uniform classification across geographic regions. The intermediate depth range does not include the deepest portions of the ocean floor. It also excludes surface and near-surface waters by definition. Its position remains fixed relative to vertical distance rather than location. This range forms a distinct segment in depth-based categorization schemes. It separates shallow classifications from deeper, mid-ocean and abyssal ranges. Depth values in this interval contribute to overall vertical variability of the ocean. The intermediate depth range is identified solely through measured depth. No additional criteria are required for its classification. Its numerical limits remain stable in international oceanographic references. The deep water depth range occupies a large portion of the global ocean vertical scale. This range is commonly defined as extending from approximately 1,000 meters to about 6,000 meters. The upper boundary follows the lower limit of intermediate depth classification. The lower boundary precedes the deepest trench-based categories. The deep water range includes most of the ocean floor by total area. Large expanses of the seafloor fall within this vertical interval. Depth values in this range are measured relative to mean sea level. Numerical limits are applied uniformly across ocean basins. This range is frequently associated with abyssal classifications in global references. Some frameworks subdivide the deep water range into smaller numerical intervals. Despite subdivision practices, the overall depth span remains consistent. Depth thresholds rely solely on vertical distance measurements. Global bathymetric datasets repeatedly show extensive coverage within this range. Broad plains and basin floors are typically located between these depth limits. The horizontal distribution varies between basins, but follows the same depth criteria. No geographic restriction is applied to its classification. The deep water range excludes surface and near-surface intervals by definition. It also excludes the most extreme depths found in narrow trench systems. Its position within the vertical scale remains fixed and measurable. Depth contours marking 1,000 meters and 6,000 meters are commonly used as references. These contours appear consistently in global mapping products. The deepwater range provides a central reference for large-scale depth comparisons. This depth range represents a substantial segment of the ocean's vertical dimension. Its numerical span contributes significantly to overall depth variability. The deepwater classification is defined entirely through standardized depth alerts. The very deep depth range occupies the lowest segment of the global ocean vertical scale. This range is commonly defined as extending from approximately 6,000 meters to the deepest measured points. The upper boundary aligns with the lower limit of deep water classification. The lower boundary reaches slightly beyond 11,000 meters in the deepest locations. This interval is often referred to as the Hadal depth range in scientific classification systems. The term is applied based on numerical depth limits rather than geographic extent. The depth values in this range are measured downward from mean sea level. Standard references place the deepest recorded values near 10,900 meters. The very deep range is geographically limited in horizontal extent. It occurs primarily in narrow, elongated depressions rather than broad basin floors. These depressions are distributed unevenly across the global ocean. Most are located in specific regions of the Pacific Ocean. Despite limited surface coverage, the depth values themselves remain clearly defined. Global bathymetric charts mark this range using contours deeper than 6,000 meters. The depth thresholds remain consistent across international datasets. No adjustment is made for regional variation in naming conventions. The very deep range excludes all intermediate and deepwater intervals by definition. It represents the extreme end of ocean depth measurements. Its numerical span exceeds 4,000 meters from upper to lower boundary. Only a small fraction of the ocean floor lies within this depth classification. Its identification relies solely on measured vertical distance. No additional criteria are applied in defining this range. The very deep depth range completes the full vertical classification of ocean depths. It provides an upper limit reference for global depth measurement systems. Extreme depth records define the lowest measured points within the global ocean. These records are based on direct depth measurements, reference to mean sea level. The deepest confirmed values occur in narrow trench systems. The most frequently cited maximum depth is located in the western Pacific Ocean. This location is commonly known as Challenger Deep. Recorded depth values at this site range between approximately 10,900 and 10,935 meters. Small numerical differences reflect measurement method and reference model. Other trench locations register depths exceeding 10,000 meters. These values remain lower than the maximum Pacific record. All confirmed extreme depths fall within the very deep classification range. Extreme depth records are reported as point measurements rather than area averages. They represent localized vertical minima rather than regional depth characteristics. Horizontal extent is limited to narrow segments of trench systems. Depth records are updated as measurement technology improves. Earlier records relied on cable soundings with wider uncertainty ranges. Modern values are derived from high-resolution acoustic surveys. Despite improved precision, reported values remain within a narrow numerical band. Extreme depth measurements are expressed in meters as the standard unit. Conversion to kilometers places the deepest records slightly above 11 kilometers. These values exceed the vertical relief of any continental land surface. No ocean basin outside the Pacific has produced a deeper confirmed record. Depth values above 10,000 meters are absent from Atlantic and Indian basins. Southern ocean measurements remain well below extreme record thresholds. Extreme depth records serve as upper limit references for ocean depth classification. They define the maximum vertical extent of the ocean. These records remain isolated cases within the overall depth distribution. The surface-associated layer occupies the uppermost vertical segment of the ocean. This layer extends from the sea surface to a depth of approximately 200 meters. The upper boundary is fixed at 0 meters by definition. The lower boundary aligns with a widely used numerical threshold in vertical classification. This layer is commonly referred to as the epipelagic layer in depth-based frameworks. The naming convention reflects vertical position rather than functional attributes. Depth values are measured downward from mean sea level. The thickness of this layer remains consistent across global references. The surface-associated layer is present across all ocean basins. Its vertical limits do not vary by geographic location. Local conditions do not alter its numerical depth bracket. Only measured depth determines inclusion within this layer. Global ocean maps frequently depict this layer as a continuous upper band. Bathymetric charts mark its lower boundary at the 200-meter contour. This contour appears consistently in international mapping products. The layer occupies a relatively small fraction of the total ocean depth. Despite limited vertical extent, the surface-associated layer spans large horizontal areas. It follows the contours of the ocean surface across the planet. Continental margins and open ocean regions both include this layer. No separation occurs between basins at this vertical level. The surface-associated layer is distinct from deeper vertical divisions. Depths greater than 200 meters fall outside this classification. The transition at the lower boundary marks a change in layer designation. This layer is defined solely through vertical distance measurement. No additional criteria are used in its identification. Its depth bracket remains stable in standardized ocean layering systems. The upper mid-depth layer occupies a vertical interval below the surface-associated layer. This layer extends from approximately 200 meters to about 1,000 meters in depth. The upper boundary coincides with the standard lower limit of the surface-associated layer. The lower boundary aligns with a widely used numerical threshold in vertical layering systems. This layer is commonly referred to as the mesopelagic layer in ocean depth frameworks. The term designates position within the vertical column rather than functional attributes. Depth values are measured downward from mean sea level. The vertical thickness of this layer is approximately 800 meters. The upper mid-depth layer is present in all major ocean basins. Its depth bracket remains constant across geographic regions. Local basin geometry does not alter its numerical limits. Only measured depth determines inclusion within this layer. Global bathymetric representations identify this layer using depth contours. The 200-meter and 1,000-meter lines serve as consistent reference markers. These contours appear uniformly in international mapping products. Layer boundaries remain standardized across datasets. This layer occupies a larger vertical span than the surface-associated layer. It represents a transitional segment between shallow and deeper vertical divisions. Depths outside this interval are excluded by definition. No overlap occurs with adjacent layers in standardized classifications. The upper mid-depth layer spans extensive horizontal areas of the ocean. It follows the global distribution of the ocean water column. Continental margins and open ocean regions both include this layer. No basin level separation is applied at this depth range. The upper mid-depth layer is defined solely by vertical distance. No additional criteria are applied in its identification. Its depth bracket remains stable in recognized ocean layering systems. The lower mid-depth layer occupies a vertical interval deeper than the upper mid-depth layer. This layer extends from approximately 1,000 meters to about 4,000 meters in depth. The upper boundary aligns with the standard lower limit of the upper mid-depth layer. The lower boundary precedes the onset of deeper abyssal classifications used in global frameworks. This layer is commonly referred to as the bathypelagic layer in vertical ocean layering systems. The designation reflects vertical position and numerical depth brackets only. Depth values are measured downward from mean sea level. The vertical thickness of this layer is approximately 3,000 meters. The lower mid-depth layer is present across all major ocean basins. Its depth limits remain consistent, regardless of geographic location. Local basin shape does not modify its numerical boundaries. Only measured depth determines inclusion within this layer. Global bathymetric products identify this layer using standardized depth contours. The 1,000 meter and 4,000 meter lines serve as common reference markers. These contours appear consistently across international mapping datasets. Layer boundaries are applied uniformly in comparative analysis. This layer occupies a substantial portion of the ocean's vertical dimension, expands a greater depth range than both the surface-associated and upper mid-depth layers. Depths outside this interval are excluded by definition. No overlap occurs with adjacent layers in standardized classifications. The lower mid-depth layer extends across wide horizontal areas of the ocean. It follows the continuous global distribution of the water column. Both open ocean regions and areas adjacent to continental margins include this layer. No basin-level segmentation is applied at this depth interval. The lower mid-depth layer is defined solely by vertical distance measurement. No additional criteria are used in its identification. Its depth bracket remains stable in recognized ocean layering references. The deep layer designation refers to a vertical ocean layer positioned below the lower mid-depth layer. This layer extends from approximately 4,000 meters to about 6,000 meters in depth. The upper boundary aligns with a common lower limit used for mid-depth classifications. The lower boundary corresponds to a widely recognized numerical threshold in vertical layering systems. This layer is commonly referred to as the abyssopelagic layer in standardized frameworks. The designation reflects depth position rather than any functional interpretation. Depth values are measured downward from mean sea level. The vertical thickness of this layer is approximately 2,000 meters. The deep layer designation applies across all major ocean basins. Its depth bracket remains constant, regardless of geographic setting. Regional basin geometry does not alter its numerical limits. Only measured depth determines inclusion within this layer. Global bathymetric maps identify this layer using depth contours. The 4,000 meter and 6,000 meter lines serve as consistent reference markers. These contours appear uniformly in international mapping datasets. Layer boundaries are applied consistently across comparative references. This layer occupies a significant portion of the lower ocean water column. It lies above the deepest vertical classifications used in global systems. Depth, shallower or deeper than this interval, are excluded by definition. No overlap occurs with adjacent layers in standardized models. The deep layer designation spans extensive horizontal areas of the ocean. It follows the continuous global distribution of ocean depth. Open ocean regions and areas adjacent to continental margins both include this layer. No basin-level segmentation is applied at this depth interval. The deep layer designation is defined solely by vertical distance measurement. No additional criteria are used in its identification. Its depth bracket remains stable across recognized ocean layering references. The trench-associated layer occupies the lowest vertical segment recognized in ocean layering systems. This layer extends from approximately 6,000 meters to the deepest measured ocean depths. The upper boundary aligns with the lower limit of the deep layer designation. The lower boundary reaches slightly beyond 11,000 meters in the deepest recorded locations. This layer is commonly referred to as the Hadal-Pelagic layer in standardized frameworks. The designation is based solely on depth range and vertical position. Depth values are measured downward from mean sea level. The total vertical thickness exceeds 5,000 meters in maximum extent. The trench-associated layer is geographically restricted in horizontal distribution. It occurs only in narrow, elongated trench systems. These systems are unevenly distributed across the global ocean. Most are located within the Pacific Ocean basin. Global bathymetric datasets identify this layer using depth contours deeper than 6,000 meters. These contours are consistently applied across international mapping references. The layer boundaries remain fixed, despite regional variation in trench shape. Only numerical depth determines inclusion within this layer. This layer excludes all shallower vertical divisions by definition. It represents the extreme lower end of the ocean's vertical structure. Depths above the upper boundary are assigned to other standardized layers. No overlap occurs between this layer and adjacent classifications. The trench-associated layer occupies a very small fraction of total ocean area. Its vertical extent contrasts strongly with its limited horizontal spread. This contrast is consistent across all recognized trench systems. The trench-associated layer is defined entirely by measured depth. No functional, biological, or ecological criteria are used in its identification. Its depth bracket remains stable in recognized ocean layering systems. Layer boundary reference depths define standardized vertical divisions of the ocean. These reference depths are expressed as numerical thresholds measured from mean sea level. They are used consistently across global ocean layering frameworks. The uppermost reference depth is set at 0 meters. This value marks the ocean's surface and serves as the starting point for all vertical measurements. All subsequent boundaries are measured downward from this reference. A primary boundary is placed at approximately 200 meters. This depth separates the surface-associated layer from deeper vertical divisions. It is one of the most consistently applied reference depths in ocean classification. Another widely used boundary occurs at approximately 1,000 meters. This depth marks the transition between upper and lower mid-depth layers. It is applied uniformly across major ocean basins. A further boundary is established at approximately 4,000 meters. This reference depth separates lower mid-depth layers from deeper layer designations. It appears regularly in global bathymetric datasets. An additional reference depth is set at approximately 6,000 meters. This depth marks the upper limit of trench-associated vertical classifications. It is used to distinguish deep layer designations from extreme depth intervals. The deepest reference boundary extends beyond 11,000 meters. This value corresponds to the maximum recorded ocean depths. It represents the lower limit of vertical ocean layering systems. These reference depths are fixed numerical values. They do not vary by geographic region or basin shape. They are applied independently of horizontal extent or local morphology. Their boundary reference depths allow consistent comparison across datasets. They provide a stable vertical framework for organizing ocean depth information. No additional criteria are required for their application. Surface pressure provides the baseline reference for ocean pressure measurements. This baseline is defined at the ocean surface at mean sea level. It represents the pressure exerted by the overlying atmosphere alone. We find the pressure at which pressure is ever. The standard surface pressure value is approximately 101,325 pascals. This value is also expressed as about 101.3 kilopascals. Another common unit expresses this pressure as 1 atmosphere. Surface pressure may also be stated as approximately 1.013 bars. In megapascals, the same value is about 0.101 pma. These units represent equivalent magnitudes using different measurement systems. Surface pressure serves as the zero-depth reference for ocean pressure profiles. All pressure values at depth are expressed relative to this baseline. Pressure measurements in the ocean include this surface value by convention. The surface pressure baseline remains constant for global reference purposes. Minor atmospheric variations are not reflected in standardized ocean profiles. A single reference value is used to ensure consistency across datasets. This baseline applies uniformly across all ocean basins. Geographic location does not alter the reference pressure value. Latitude and longitude are not factors in its definition. The pressure units used at the surface are identical to those used at depth. Pascal base units are common in scientific reporting. Atmospheres and bars are also widely used in comparative descriptions. Surface pressure defines the starting point of pressure magnitude ranges. It marks the lowest pressure. Its pressure defines the lowest pressure value encountered within the ocean. This reference pressure is used in charts and tables describing vertical pressure distribution. It anchors the numerical scale for all subsequent depth-related values. No additional qualifiers are applied to the surface pressure baseline. The pressure range at shallow depths covers the upper portion of the ocean water column. This range extends from the surface to depths of approximately 200 meters. Pressure values within this interval are expressed relative to mean sea level. At the ocean surface, pressure is approximately 101,325 pascals. This value is equivalent to about 101.3 kilopascals. It is also expressed as 1 atmosphere, or approximately 1.013 bars. At shallow depths below the surface, pressure values rise above the surface baseline. By a depth of around 10 meters, pressure reaches roughly 2 atmospheres. This value corresponds to approximately 202 kilohertz, or 0.2 megahertz. At depths near 50 meters, pressure is approximately 6 atmospheres. This value is equivalent to about 600 kilopascals. In megapascals, the same pressure is close to 0.6 megapascals. At the lower boundary of shallow depths, near 200 meters, pressure approaches 21 atmospheres. This magnitude corresponds to roughly 2.1 megapascals. In kilopascals, this value is approximately 2,100 kPa. Pressure values in this range are commonly reported using pascals, kilopascals, or megapascals. Atmospheres and bars are also used for comparative reference. All units describe the same pressure magnitudes using different scales. The shallow depth pressure range is applied consistently across global ocean basins. Geographic location does not alter the standardized pressure values assigned to depth brackets. Depth alone determines placement within this pressure range. This range represents the lowest segment of the ocean pressure distribution. All deeper pressure ranges exceed the upper limit defined at shallow depths. Shallow depth pressure values provide a reference band for vertical pressure classification. The pressure range at mid-depths occupies a central portion of the ocean pressure profile. This range extends from depths of approximately 200 meters to about 1,000 meters. All pressure values are referenced to mean sea level. At the upper boundary near 200 meters, pressure is approximately 21 atmospheres. This value corresponds to about 2.1 megapascals. In kilopascals, this pressure is close to 2,100 kPa. At depths around 500 meters, pressure reaches approximately 51 atmospheres. This magnitude is equivalent to about 5,100 kilopascals. The same value may also be expressed as roughly 5,100 kilohertz. Near the lower boundary at 1,000 meters, pressure approaches 101 atmospheres. This value corresponds to approximately 10,100 kPa. In kilopascals, the pressure is close to 10,100 kPa. Pressure values in this range are commonly expressed using pascals or megapascals. Atmospheres and bars are also used as comparative units. All units represent the same magnitudes using different numerical scales. The mid-depth pressure range is applied consistently across all ocean basins. Geographic location does not modify the standardized pressure values assigned to depth intervals. Only depth determines placement within this pressure range. This range represents an intermediate segment between shallow and deeper pressure classifications. All pressures within this interval exceed shallow depth values. They remain lower than pressures found in deeper and trench-associated ranges. In this statement, BC, mid-depth pressure values appear frequently in global ocean pressure charts. They provide a reference band for organizing vertical pressure data. No additional criteria leads actions of any power. Deadly. The pressure range at deep zones covers a large portion of the ocean's vertical extent. This range is commonly bracketed from approximately 1,000 meters to about 6,000 meters in depth. Per XOS. Pressure values in this interval are reported using standardized measurement units. All values are referenced to mean sea level. At the upper boundary near 1,000 meters, pressure is approximately 101 atmospheres. This magnitude corresponds to about 10,100 kPa. In kilopascals, the same pressure is close to 10,100 kPa. In bars, the value is approximately 101 bar. At a depth near 2,000 meters, pressure is approximately 201 atmospheres. This value corresponds to about 20,100 kilohertz. In kilohertz, the magnitude is close to 20,100 kPa. In bars, the value is approximately 201 bar. At a depth near 4,000 meters, pressure reaches approximately 401 atmospheres. This magnitude corresponds to about 41 megapascals. In kilopascals, the pressure is close to 40,100 kPa. In bars, the value is approximately 401 bar. At the lower boundary near 6,000 meters, pressure approaches approximately 601 atmospheres. This value corresponds to about 60,100 kPa. In kilopascals, the magnitude is close to 60,100 kPa. In bars, the value is approximately 601 bar. Megapascals and kilopascals are common units in scientific datasets. Atmospheres and bars are common reference units for comparison. All units describe identical pressure magnitudes using different numerical scales. The deep zone pressure range applies across all major ocean basins. Depth alone determines placement within this pressure interval. Pressure at maximum recorded depths represents the highest values observed within the global ocean. These pressures correspond to the deepest measured locations on the seafloor. All values are referenced to mean sea level. Maximum recorded depths occur at approximately 10,900 to 11,000 meters. At these depths, pressure approaches about 1,100 atmospheres. This magnitude reflects the upper end of measured ocean pressure ranges. In Pascal-based units, this pressure is approximately 110,000 kilopascals. The same value corresponds to roughly 1,100 bar. Reported values vary slightly depending on the exact measured depth. Differences also arise from the reference model used for depth conversion. Despite variation, all reported values fall within a narrow numerical range. Maximum pressure values are associated with point measurements rather than broad areas. They represent localized extremes rather than regional averages. No other ocean locations exceed these recorded magnitudes. Pressure at these depths greatly exceeds values found in deep and mid-depth zones. The increase relative to surface pressure exceeds 1,000 atmospheres. These values define the upper limit of the ocean pressure scale. Standard units used in reporting include megapascals, kilopascals, atmospheres, and bars. Each unit expresses the same magnitude using a different numerical format. Scientific datasets commonly present values in megapascals. No ocean basin outside the Pacific records comparable maximum pressures. Atlantic and Indian Ocean values remain substantially lower. Southern Ocean measurements do not approach maximum depth pressure levels. Pressure at maximum recorded depths provides a terminal reference for vertical pressure classification. It marks the highest confirmed pressure encountered in the ocean. No additional criteria are applied beyond measured depth and standardized units. Pressure unit conventions define standardized ways to report ocean pressure. Labels continued. These conventions were shaped in the acting space of companies. These conventions apply across all depth ranges in the global ocean. They ensure consistency between datasets and comparative. The primary scientific unit for pressure is the Pascal. 1 Pascal equals 1 Newton per square meter. Because ocean pressures are large, derived units are commonly used. Kilopascals are frequently used for shallow and mid-depth reporting. 1 kilopascal equals 1,000 pascals. Megapascals are commonly used for deep and extreme depth values. 1 megapascals equals 1 million pascals. Another widely used unit is the atmosphere. 1 atmosphere corresponds to approximately 101,325 pascals. Atmospheres provide a convenient comparative scale for depth-related pressure. The bar is also used in oceanographic reporting. 1 bar equals exactly 100,000 pascals. In many contexts, bars and atmospheres appear with similar numerical values. Pressure values may also be expressed using pounds per square inch. This unit is less common in scientific oceanography. It appears primarily in engineering or technical references. All pressure units describe the same physical quantity. Differences arise only from numerical scaling and unit definition. Conversion between units follows fixed mathematical relationships. Ocean pressure values are always reported as absolute pressure. The surface atmospheric pressure is included in reported values. Gauge pressure conventions are not used in standard ocean datasets. Depth-related pressure tables typically list values in multiple units. Megapascals, atmospheres, and bars often appear together. This practice supports cross-disciplinary comparison. Pressure unit conventions do not vary by ocean basin. They are independent of geographic location. They apply uniformly from the surface to maximum recorded depths. Pressure unit Sephiros. Standardized units provide a consistent framework for describing vertical pressure distribution. They allow pressure magnitudes to be compared across depth ranges. No additional qualifiers are required beyond unit specification. Sea level serves as the primary reference point for vertical ocean measurements. It defines the zero point from which ocean depth and elevation values are calculated. This reference is used consistently in global oceanographic datasets. Mean sea level represents an averaged surface position over a defined time period. It accounts for short-term variability by using long-duration observations. The averaging period typically spans multiple years. A series of crash to the end. Mean sea level is not identical to the instantaneous ocean surface. Waves, tides, and short-term fluctuations are excluded from the reference definition. Only the averaged level is used as the vertical baseline. Vertical measurements below sea level are expressed as positive depth values. Measurements above sea level are expressed as elevations. This convention allows uniform treatment of land and ocean surfaces. Global sea level reference systems rely on standardized geodetic models. These models align ocean measurements with Earth-centered coordinate frameworks. Consistency between regions is maintained through shared reference definitions. Sea level reference values are applied across all ocean basins. They do not vary based on local coastal conditions. Regional differences in tidal range do not alter the global reference. Bathymetric maps use sea level as the zero-depth contour. All depth contours are measured downward from this reference. Comparisons between basins depend on this common baseline. Satellite altimetry and ship-based surveys both adopt sea level references. The reference allows integration of data from different measurement platforms. Depth values remain comparable across observation methods. Sea level reference definitions are periodically refined. Refinements improve global consistency rather than altering the conceptual baseline. Historical datasets are adjusted to align with updated reference models. The sea level reference establishes the starting point of the ocean's vertical scale. It anchors depth classification, pressure calculation, and vertical mapping. No additional contextual qualifiers are required for its use. Depth measurement units provide standardized ways to express vertical distance in the ocean. These units are applied consistently across global oceanographic datasets. They define how depth values are recorded and compared. The primary unit used in scientific reporting is the meter. 1 meter represents the base unit of length in the International System of Units. Most ocean depth values are recorded directly in meters. For large depth values, kilometers are also used. 1 kilometer equals 1,000 meters. Kilometers are commonly applied when expressing total depth span, or extreme depths. In some regional or historical contexts, depth may be expressed in feet. 1 foot equals approximately 0.3048 meters. This unit appears mainly in legacy charts or non-scientific references. Nautical charts may also reference fathoms. 1 fathom equals 6 feet, or approximately 1.808 meters. Fathoms are primarily used in navigation-related materials. Scientific datasets favor metric units for consistency. Meters and kilometers allow direct integration with other geophysical measurements. They align with pressure, distance, and scale conventions used in ocean studies. Depth values are always reported as positive numbers below sea level. The unit specifies magnitude rather than direction. The reference point remains mean sea level. Conversion between depth units follows fixed numerical relationships. These relationships do not vary by location or ocean basin. Standard conversion factors are applied universally. Depth measurement units do not encode additional information. They represent vertical distance only. Interpretation depends solely on the numerical value and reference point. Standardized units ensure comparability across maps, charts, and datasets. They support consistent representation of the ocean's vertical scale. No additional qualifiers are required beyond unit specification. Vertical datum usage establishes the reference framework for measuring ocean depth. A vertical datum defines the zero level from which vertical distances are calculated. In oceanography, this datum is tied to a standardized sea level reference. Mean sea level is the most commonly used vertical datum for ocean depth reporting. It represents an averaged reference surface derived from long-term observations. This datum provides a stable baseline for global comparison. Depth values are expressed as positive distances measured downward from the datum. The datum itself is assigned a value of 0 meters. All reported depths depend on this fixed reference point. Vertical datums are applied consistently across global bathymetric datasets. They allow depth values from different regions to be compared directly. Without a shared datum, numerical depth values would lack alignment. Multiple geodetic datums exist within Earth measurement systems. Ocean depth datasets specify the datum used to ensure clarity. Standard practice favors globally recognized reference models. Vertical datum definitions are independent of local shoreline position. Coastal water level variation does not alter the global datum reference. Bathymetric charts explicitly reference their chosen vertical datum. Depth contours are calculated relative to this reference surface. Comparisons between charts require consistent datum usage. Satellite-derived ocean measurements also rely on defined vertical datums. These datums align satellite observations with ship-based depth records. Consistency across measurement platforms is maintained through shared references. Vertical datum usage does not describe how measurements are obtained. It specifies only the reference level for numerical depth values. Instrumentation details are separate from datum definition. Updates to vertical datums occur as global reference models improve. Such updates refine alignment rather than change the conceptual baseline. Depth values may be adjusted to remain consistent with revised datums. Vertical datum usage provides a common framework for the ocean's vertical scale. It supports standardized mapping, classification, and comparison. No additional criteria are required beyond clear datum specification. Depth rounding conventions define how numerical depth values are presented in ocean datasets. These conventions apply after depth values are measured and referenced to a vertical datum. They standardize numerical expression rather than altering underlying measurements. Rounding is commonly applied to match the scale of the dataset. Large-scale global maps often round depths to the nearest 10 or 100 meters. Regional datasets may use finer rounding increments. In scientific reporting, depth values are frequently rounded to whole meters. This convention balances numerical clarity and data volume. The scuminal fractions of a meter are usually omitted in published summaries. For extreme depths, rounding to the nearest 10 meters is common. This practice reflects the scale of global depth variation. It also aligns with typical uncertainty ranges in compiled datasets. Kilometer-scale summaries often round depths to 2 or 3 decimal places. This approach is used when expressing depth in kilometers rather than meters. The chosen precision reflects the intended level of comparison. Depth contours on maps follow fixed rounding intervals. Contour lines are typically drawn at regular depth increments. Common intervals include 100 meters, 500 meters, or 1,000 meters. Rounding conventions are applied consistently within a single dataset. They are documented to ensure correct interpretation. Users rely on stated conventions when comparing values across sources. Rounding does not imply reduced measurement capability. It reflects choices made during data presentation and aggregation. Original measurements may retain higher numerical precision internally. Different datasets may use different rounding standards. Comparative analysis requires awareness of these differences. Direct comparison assumes compatible rounding practices. Depth rounding conventions do not change reference points or units. They modify only the displayed numerical value. The underlying depth scale remains unchanged. Standardized rounding supports clear communication of depth information. It reduces visual and numerical complexity in large datasets. These conventions form part of the broader vertical measurement framework. Global depth comparison standards define how ocean depths are evaluated across regions. These standards establish uniform reference conditions for vertical comparison. They allow depth values from different basins to be assessed on the same scale. The primary standard uses mean sea level as the common vertical reference. All depth values are measured downward from this reference point. This approach removes regional variation in surface conditions. Depth comparisons rely on metric units as the global norm. Meters serve as the base unit for detailed comparison. Kilometers are used for summarizing large vertical spans. Standardized depth ranges are used to group values for comparison. The border motorist meter. Common ranges include surface, mid-depth, deep, and extreme categories. Each range is defined by fixed numerical boundaries. Global bathymetric datasets apply these standards consistently. Depth values are aligned to shared vertical datums. Comparability is maintained across mapping products and databases. Comparison standards do not depend on geographic proximity. Depth values from distant ocean basins are evaluated equivalently. Latitude and longitude do not alter the comparison framework. Global standards also define how maximum and minimum depths are compared. Extreme values are reported using the same reference scale. This ensures that depth records are directly comparable. Depth comparison standards are documented in dataset metadata. They specify reference points, units, and rounding practices. Users rely on these specifications for accurate interpretation. International organizations maintain shared comparison conventions. These conventions support collaboration across research institutions. They reduce ambiguity in global depth reporting. Comparison standards do not prescribe measurement methods. They address only how depth values are referenced and compared. Instrumentation details are excluded from the standard definitions. Global depth comparison standards provide a stable framework. They support consistent evaluation of the ocean's vertical scale. No additional criteria are required beyond adherence to shared references. Depth record documentation defines how ocean depth values are formally recorded and referenced. These records provide a standardized account of measured depth information. They support long-term comparison and archival use. Depth records specify the numerical depth value and the associated unit. Meters are used as the primary unit in scientific documentation. Kilometers may appear for summary descriptions of extreme depths. Each record includes a defined vertical reference. Mean sea level is identified as the zero depth datum. This reference ensures consistency across datasets. Depth record documentation distinguishes between point measurements and aggregated values. Point records represent specific locations on the seafloor. Aggregated records summarize depth over defined areas. Records identify whether a value represents a maximum, minimum, or representative depth. Maximum depth records correspond to the deepest confirmed measurements. Minimum values describe shallow reference limits within a dataset. Documentation includes the geographic context of the depth record. Location is expressed through coordinates or basin identifiers. This information supports spatial comparison without altering depth values. Depth records state the rounding or precision applied. Whole meters are commonly used in published records. Rounding conventions are noted to support interpretation. Temporal context is included in depth record documentation. The date or period of measurement is recorded. This allows alignment with reference models used at the time. Depth records reference the dataset or survey from which values originate. This citation supports traceability and verification. It does not describe measurement procedures. Revisions to depth records are documented when reference models change. Updated records maintain continuity with earlier datasets. Historical values may be adjusted to align with revised standards. Depth record documentation follows consistent formatting conventions. These conventions enable comparison across institutions and regions. They support integration into global depth compilations. Documented depth records form a stable foundation for vertical scale analysis. They allow the ocean's depth range to be compared over time. No additional information is required beyond standardized documentation elements. Ocean depth represents a small vertical fraction of the planet's overall dimensions. The maximum measured ocean depth reaches slightly beyond 11 kilometers. This value is measured relative to mean sea level. Earth's average radius is approximately 6,371 kilometers. The deepest ocean depth represents less than 0.2% of this radius. When compared to planetary diameter, the proportion is even smaller. The ocean's vertical extent is also minor relative to Earth's circumference. Earth's equatorial circumference measures about 40,075 kilometers. The full depth of the ocean occupies a narrow vertical interval within this scale. Comparisons are often made between ocean depth and continental elevation. The highest continental elevations reach just under 9 kilometers above sea level. The deepest ocean depths extend several kilometers beyond this value in the opposite direction. When the planet is visualized at global scale, ocean depth appears as a thin surface layer. The majority of Earth's volume lies far below the deepest seafloor. The ocean occupies a shallow external shell relative to planetary size. Temporal stability is observed in this proportional relationship. Measured ocean depths have remained within similar numerical limits across recorded history. Improvements in measurement refine values without altering the scale comparison. Large-scale planetary models often represent the ocean as a surface boundary condition. Depth values are treated as small perturbations relative to Earth's radius. This approach supports consistent global modeling frameworks. Despite limited proportional thickness, the ocean spans most of the planet's surface area. Horizontal coverage contrasts with limited vertical reach. This contrast remains consistent across time-based global references. Ocean depth relative to planetary dimensions provides a stable spatial context. It situates vertical ocean measurements within Earth-scale geometry. This reference supports comparison without invoking geological mechanisms. Ocean depth ranges show long-term persistence when viewed at planetary scale. The numerical limits used to describe shallow, intermediate, deep, and extreme depths remain stable across historical records. These ranges are defined by vertical distance rather than short-term variation. Recorded ocean depths from early surveys fall within the same broad brackets used today. Subsequent measurements refine precision without redefining overall depth categories. Maximum and minimum depth values remain within comparable numerical bounds over time. Shallow depth ranges have consistently been identified within the upper few hundred meters. Intermediate ranges continue to occupy depths between several hundred and several thousand meters. Deep and extreme ranges persist at depths exceeding several kilometers. Temporal comparison shows that the deepest known points have remained within a narrow interval near 11 kilometers. No evidence suggests a shift beyond this scale in recorded observations. Updates to depth values reflect improved resolution rather than expansion of range. Large-scale depth classifications are maintained across successive mapping generations. Global bathymetric compilations from different decades use similar vertical thresholds. This consistency supports direct comparison between historical and modern datasets. Persistence is also observed in the relative proportion of depth ranges. The majority of the ocean floor remains within deep water categories across time-based records. Shallow and extreme depth areas continue to occupy smaller proportions by area. Temporal datasets treat depth ranges as stable reference frames. They are used to align observations collected at different periods. This approach allows long-term comparison without reclassification. Adjustments to reference models do not alter the fundamental depth brackets. They improve alignment between datasets while preserving scale. Depth range definitions remain anchored to fixed numerical intervals. The persistence of depth ranges provides continuity in ocean description. It allows vertical structure to be compared across decades of observation. This stability supports large-scale analysis without invoking geological change. Maximum depth stability records describe how the deepest known ocean values have remained within a limited numerical interval across successive surveys. The deepest confirmed measurements consistently occur in trench systems of the Western Pacific. The most frequently cited site is Challenger Deep. Published maximum depth values are commonly reported between approximately 10,900 meters and 10,935 meters. This interval reflects differences among datasets rather than changes in ocean geometry. Reported maxima remain centered near 10.9 kilometers when expressed in kilometer units. Early cable sounding records produced maximum depth estimates that fell within the same 10.8 to 11.0 kilometer scale. Later, acoustic survey compilations refined the numerical value while retaining the same order of magnitude. Modern high-resolution bathymetric products continue to report maxima within a narrow band near 11 kilometers. Maximum depth stability is also expressed through the persistence of the 6,000-meter threshold as the upper boundary of trench association classifications. All maximum depth records fall well below this boundary and occupy the extreme end of the vertical scale. No other ocean basin has produced a confirmed maximum that exceeds the Western Pacific record. The numerical stability of maximum depth reporting is reinforced by repeated independent surveys. Multiple compilations list comparable maxima even when produced in different decades. Small variations in reported depth values arise from reference model choice, gridding methods, and rounding conventions. The maximum depth record is documented as a point value rather than an area average. The surrounding region includes depth contours that constrain the maximum within limited spatial extent. Repeated mapping continues to place the global maximum within the same localized trench system. Maximum depth stability records provide a consistent upper bound for global depth comparisons. They anchor the extreme end of ocean depth range classifications. They remain compatible across historical and modern bathymetric references. Vertical scale varies across the major ocean basins, while remaining within a shared global framework. Each basin exhibits a characteristic range between surface level and its deepest mapped points. These ranges are described using consistent reference standards. The Pacific Ocean contains the greatest vertical extent among the basins. Its maximum recorded depths exceed 10,900 meters. Average basin depths are also greater than those of other oceans. The Atlantic Ocean displays a smaller overall vertical range. Its deepest points reach approximately 8,700 meters. Large areas of the Atlantic Basin occupy mid-depth ranges rather than extreme depths. The Indian Ocean presents an intermediate vertical scale. Its maximum depths approach approximately 7,300 meters. The majority of its basin area lies within deep but non-trench classifications. The Southern Ocean surrounds Antarctica and shows a continuous circumpolar depth profile. Maximum depths in this basin reach approximately 7,200 meters. Its vertical scale reflects broad, deep areas rather than narrow, extreme points. The Arctic Ocean has the smallest vertical extent of the major basins. Its deepest regions reach approximately 5,500 meters. Large portions of the Arctic Basin occupy comparatively shallow depth ranges. Despite these differences, all basins share common depth category boundaries. Surface, mid-depth, deep, and trench-associated ranges are defined using the same numerical thresholds. This allows direct comparison of vertical scale across basins. Temporal records show that these basin-specific depth ranges remain stable. Successive mapping efforts refine measurements without altering relative ordering. The Pacific consistently retains the greatest vertical extent, and the Arctic the smallest. Vertical scale comparison across basins highlights contrast without requiring process explanation. It situates each basin within a shared global depth framework. This approach supports long-term comparison across space and time. Depth distribution statistics summarize how ocean depths are proportionally arranged across the global seafloor. These statistics describe the relative prevalence of different depth ranges rather than individual locations. Values are derived from compiled global bathymetric datasets. The mean depth of the global ocean is approximately 3,700 meters. This average reflects the dominance of deep basin floors across ocean area. Median depth values fall within a similar range, indicating limited skew from extreme depths. Shallow depths occupy a relatively small fraction of total ocean area. Depths shallower than 200 meters account for less than 10% of the seafloor. These areas are concentrated along continental margins and shelf regions. Intermediate depths between 200 meters and 1,000 meters represent a modest proportion. This range occupies a larger area than shallow zones, but remains secondary in coverage. Its spatial distribution follows continental slope regions worldwide. Depths between 1,000 meters and 6,000 meters dominate global area statistics. This interval accounts for the majority of the ocean floor by surface area. Large abyssal plains contribute significantly to this distribution. Very deep depths beyond 6,000 meters represent a small fraction of total area. These depths are confined to narrow trench systems. Their limited horizontal extent contrasts with their large vertical magnitude. Depth frequency distributions show a strong peak within deep water ranges. Frequencies decrease sharply toward both shallow and extreme ends of the scale. This pattern remains consistent across successive global compilations. Statistical summaries often report depth ranges alongside percentage area coverage. These summaries support comparison between basins and time periods. They rely on standardized depth brackets and reference models. Depth distribution statistics remain stable across updated data sets. Refinements alter resolution rather than proportional structure. This stability supports long-term comparison of the ocean's vertical arrangement. Long-term depth reference datasets provide standardized records of ocean depth over extended periods. These datasets compile measurements collected across decades of observation. They support consistent comparison of ocean depth at global scale. Global reference datasets use a common vertical datum based on mean sea level. Depth values are reported as vertical distance below this reference. This approach maintains alignment between historical and modern records. Major depth datasets are assembled through international collaboration. They integrate measurements from multiple surveys and time periods. Compilation methods emphasize consistency of reference rather than measurement technique. Depth reference datasets retain stable numerical frameworks across revisions. Updates refine spatial resolution and coverage without redefining depth scale. Previously reported depths remain comparable after dataset revision. Temporal continuity is a defining feature of long-term depth references. Depth ranges used in early compilations persist in modern datasets. Shallow, deep, and extreme depth categories retain fixed numerical limits. Maximum and minimum depth records are tracked within these datasets. Extreme values are preserved as reference points across successive versions. Small numerical adjustments do not alter overall depth range classification. Long-term datasets support comparison between ocean basins. They apply uniform depth brackets to all regions. This allows vertical scale comparison across space and time. Depth reference datasets are distributed in standardized digital formats. These formats include metadata, describing reference systems and units. Documentation ensures transparency of depth values across versions. Historical depth records are retained alongside updated values. This practice preserves continuity for long-term analysis. Researchers can align older datasets with newer compilations. Long-term depth reference datasets do not describe physical change mechanisms. They provide numerical context for vertical scale comparison only. Geological interpretation is excluded from dataset definition. These datasets form the foundation for temporal analysis of ocean depth. They anchor comparisons across decades of observation. Their stability supports consistent representation of the ocean's vertical extent. Depth remains a vertical reference within a fluid continuum. Measurements persist as relational markers across varying scales without fixed termination. The gradient extends beyond any single point of observation, and then